We present a computational design tool for creating multi-stable mechanisms. In this example, we used our tool to design a compliant bar joint mechanism that exhibits three iconic poses of famous athletes: Usain Bolt, Michael Jordan, and Tiger Woods. While each pose is stable against disturbances forces, we still ensure that the mechanism can be transitioned from one pose to the other. Before showing more examples, we describe the main aspect of this work. Our research is inspired by graph rigidity theory. A general graph can be flexible, locally rigid, or globally rigid. Among them, flexible graphs are not stable and can be deformed continuously. Globally rigid graphs, in contrast, exhibit only a single stable configuration. We identified minimally rigid graphs as a fitting concept for our mechanisms, as they exhibit a finite set of stable poses. Given such a minimally rigid graph, we transform it into a compliant bar joint mechanism by converting edges into rigid and compliant bars with hinge joints between them. In its rest shape, such a mechanism is stably located at a local minimum of its elastic energy. By bending the compliant bars, the mechanism can be switched into a different stable pose by overcoming the energy barrier between these poses. Each of these stable poses lies at a local elastic energy minimum, and our design tool identifies a mechanism that reproduces the desired positions in each pose. Furthermore, it is ensured that the mechanism can be transitioned between all desired poses. In our inverse design framework, we design both the graph and the mechanism based on user specifications. As input, the user specifies the desired poses of relevant end effectors, here shown in orange. Our algorithm then discovers suitable minimally rigid graphs and optimizes the edge length for each of the corresponding bars. Overall, it searches for the best graph topology and bar lengths to not only approximate the user-provided target poses as close as possible, but also to ensure sufficient rigidity of the mechanism in each stable pose. As a post-process, we generate fabricable bar joint mechanisms for both 3D printing and laser cutting. We used our implementation to design several multi-stable structures and validated their applicability by fabricating physical prototypes. In this example of the multi-stable figurine, both symmetric arm and asymmetric leg movements are correctly synchronized by our design. Note that the mechanism automatically moves into the stable pose after the energy barrier between two poses is crossed. In this example, letters are mapped to the flag semaphore, a traditional way of naval communication. Each letter and number corresponds to a certain positioning of both flags. Here we show the three-letter combination S-I-G. Again, our physical prototype closely matches the desired flag positions in each of the three stable poses. We also successfully designed the multi-stable mechanisms for thousands of letter combinations to validate the robustness of our approach. These are shown in the result gallery in the supplemental material. This example shows that complex real-world motion of human characters can be faithfully replicated by our system. Now, while all previous examples were 3D printed, this gripper prototype was manufactured using laser cutting. By ensuring sufficient stability of each pose, our system equips the gripper with sufficient carrying capacity to handle small loads. Thank you for your attention.